All right, so finally, at this point in the year, and what is it, March now? We started in September, and now, just now, we are finally getting to the fundamental theorem of calculus. Okay, and this is going to just kind of relate the derivative and the integral, and we've already kind of seen that relationship a little bit. We know that they're just inverses, and one of the guys who discovered that here is Isaac Barrow, and so you can read all that. I don't want to waste your time in this video. So now we're ready for the shortcut rule. You practice Riemann sums and adding all the rectangles, and now we're trying to look for an easier way. All right, and here's a table, and these are basic ones, and this is what we'll practice with, so hopefully you know your derivatives so you can undo them. If you don't know your derivatives, you're going to have a really tough time. All right, so just talking about a couple of these. This one, we have that constant there that we can just pull out. If we take the integral of a constant, remember that would just look like a line, so it's just the constant times x. This is our like reverse of the power rule. E to the x, that's a nice easy one. And notice, sorry, right here, and it can't be -1. We can't do x to the -1. And the reason why is because if we integrate that, we'll get x to the 0, and that doesn't make sense. That's where our ln of x function comes in. All right, so we have sine, secant squared, secant tangent, 1 over x squared plus 1, all of those trig over here. Any of these trigs, these are things you have to know, okay? And these aren't the only ones. And then here, if we have two terms that you're adding or subtracting, you can break that up into two separate integrals. And this is one that we saw in class a few days ago, where we had to divide by the ln of the base. All right, so let's take a look here. This is finally the fundamental theorem of calculus. And you don't want to have to say that every single time. FTOC 1, part 1. All right, if a function f, little f, is continuous on a closed interval, and big F of x is an antiderivative of f, then this integral of little f from a to b, the net accumulation from a to b on f of x, can be big F of x, okay, evaluated from a to b there, so that means you take the f of b minus f of a. Okay, and this is the shortcut that we've been practicing. All right, so evaluate the integrals here using this. So we need to find the antiderivative of this, which would just be e to the x minus 3x. And now we need to evaluate it from 1 to 3. All right, so anytime you're doing this, you want to set up your two sets of parentheses. So e cubed minus 9, okay, minus e to the first minus 3. I'm going to make this a little bit smaller here. Okay. So this will be e cubed minus 9 minus e plus 3. And if you want to rewrite it, e cubed minus e minus 6. And this is something that you can check in your calculator. You can type it right in, and you should get the same exact thing. All right, this one, if you know, I'm just going to rewrite it up here. If you know your derivatives, this one is very simple. I'm going to pull that 2 out. Okay, and then what's left? 1 minus, there we go. Now, if you know your antiderivatives, you know that that would just be inverse sine. Okay, so bring that constant factor out, inverse sine of x, and we're going to evaluate it from 0 to 1/2. And hopefully you do know how to remember how to evaluate these. So inverse sine of 1/2. Here's my two sets of parentheses, minus inverse sine of 0. So where is the sine function equal to 1/2? Okay, that's 1/6 pi. And where's the sine function equal to 0, which would be that? So our last answer is pi over 3. And again, it's a good practice to check it on your calculator. Okay, make sure you know how to use your calculator. The more you use it, the better you're going to get it. All right, x to the -1. Can we use the power rule here? No, we can't. All right, you have to recognize this. So the antiderivative of that is ln, absolute value of x, and we're going to evaluate that from 1 to e squared. Okay, so we get ln of e squared minus ln of 1. All right, now using properties of logs here, ln of e squared, that's just 2. Okay, you can bring the 2 to the front, and ln of e is just 1. Minus ln of 1 is 0, so this one is simply 2. All right, let's try a couple more here. So evaluate these using any method. Let's see, which one would I like you guys to do? I want you to try letter A. This will be your whisk thing, okay? And I'm going to go ahead and do the other ones. So let's do part B first. I'm going to pull out that constant, and I'm going to rewrite it as x to the 1/2. All right, add 1 to the power, divide by the new power. Okay, so I'll get 2/3 x to the 3/2, evaluated from 1 to 4. So 3 times, let's see, this was 4 to the 3/2. That'll be 2 cubed 8. So we'll get 2/3 times 8 minus 2/3. So 3 times 16/3 minus 2/3. 3 times 14/3, or just 14. All right, secant squared of x, if you know that antiderivative, this is an easy problem. All right, that's going to be tangent of x evaluated from 0 to 1/4 pi. So tangent of 1/4 pi minus tangent of 0. Well, the tangent of 1/4 pi, that's just 1. Tangent of 0 is 0, so our answer in this case is 1. Now the last one I think is probably the neatest, because you look at it and you say, oh man, I don't know how to integrate something like that. But then you remember that this isn't the only way, okay? One way that you could do this is by drawing a picture. All right, you know what 2x minus 1 looks like. It's just an equation. It would look something like this, okay? But it's the absolute value of that. So anything below the x-axis is just going to flip up. All right, so it's going to look something like this. So we're trying to find that net accumulation, that area from 0 to 2. All right, and so it would meet over here at 1/2. We're going up to 2. And from 0. So we're looking for this area. Okay, so from here to here, which is just 2 triangles, right? So let's find out where that would cross at, that would be 1, right? And then this height, if you plug in 2, you get 3. So the area is going to be equal to 1/2 times base, which is 1/2 times the height, plus 1/2 times, let's see, this, from 1/2 to 2, that's going to be 3/2, or 1.5, times the height, which is 3. All right, so we get 1/4 here, plus, is that 9/4, which is the same as 10/4 or 5/2. And if you type that into your calculator, you should see that we got the same exact answer your calculator would. Although this one was a little bit easier doing it by a graph than it was by finding the antiderivative. All right, so this last one, maybe the last one. Yeah, sure, let's go with that. This will be the last one. Find the exact value of this monstrosity of an equation. All right, so I'm going to rewrite this a little bit. 10x to the 4th, no problem with that. And again, you could break this up because we have 3 separate terms if you want to break it up. I'm going to just leave it all together. Why not? All right, minus 2 times, that's 1 over 1 minus x squared. That looks familiar. I mean, square root of that, sorry. Minus 5 over x, and there should be a dx there. All right, now, antiderivative. Add 1 to the power, divide by that new power, 2x to the 5th. Minus 2 times, do you recognize that function there? That's our inverse sign again. And this, can't add 1, divide by the new power. This will be 5 times ln of absolute value of x. And we want to evaluate this thing from 1/2 to 1 over e. So you just plug it in. All right, so we get 2 e to the, and I'm going to say -5th here. Instead of writing 1 over e to the 5th, I'm going to write e to the -5th. Minus 2 times inverse sine of 1 over e. Let's see, what is 5 times ln of 1 over e? That's 5 times ln of e to the -1. Okay, or -5 times ln of e, which is just -5. All right, so it's minus a -5, which will give us a +5. So we did the first part. Now we're going to do the second part. 2 times 1/2 to the 5th. That'll be 2 times 1 over 32. Minus 2 times inverse sine of 1/2. Minus 5 times ln of 1/2. All right, so combining, maybe rewriting some of this. I like to write it like this. All right, minus, we can't really do anything with that. We'll just leave it. Plus 5 minus 1 over that. Okay. Oh, do you remember this? Where is sine equal to 1/2? That would be pi over 6, right? And then 2 times that, so that would be pi over 3. And we could just leave this alone. There you go. That is your answer. What a beautiful thing. And I think this will be a pretty good place to stop. If you were doing this on an AP exam, you could have stopped right there. Because it you don't have it written with any variables, okay, and everything's just there to be multiplied out. So why don't you pick a couple of problems on your worksheet? All right, I have a few that I think look just like this, but I think you'll find them, and come in with questions tomorrow.